Alright, this video is talking about the equation derivation with isotope doping methods. The following equations is used to depict the dissolution rate and precipitation rates in a bench system. I will walk through some of the deduction details and to get you some intuitive sense about this. For example, we have a bench system. We have the mineral in it. Let's see, it's a dark mineral, and we have the solution. Because we doped the solution with 29, and the dark mineral is enriched in 28, so we can describe the mass balance of 28 and the 29 separately. So the 28 silicate at time t plus 1 equals the 28 silicate at time t plus the dissolution of 28, which is the rate of dissolution times the fraction of 28 in the solid times delta t minus the precipitation of 28, which is the rate of precipitation times the fraction of 28 in the solution times delta t. And we can simplify this equation 1 as follows. The 28 silicate t plus 1 minus 28 silicate at time t over time t delta t can be simplified as d 28 silicate over dt equals the dissolution of 28 minus the precipitation of 28. Using the same process, we can get that 29 silicate at t plus 1 minus the 29 silicate at time t over delta t equals d 29 silicate over dt equals rate of dissolution of 29 minus the precipitation of 29. So we can describe the dissolution rate in equation 2. So from equation 2, the dissolution rate RDIS equals d28 over dt plus rate of precipitation over the fraction of 28 in the solid. And we can substitute the dissolution rate in equation 3 with equation 4. Then we can get rate of precipitation equals d29 silicate over dt minus the dissolution rate actually equals the RDIS times the fraction of 29 in solid minus d29 over dt over fraction of 29 in the solution. So we can change the dissolution rate with this equation here. Then we can get the precipitation rate equals d28 silicate over dt minus d29 silicate over dt times 28 over 29 in the solid over 29 silicate times the fraction of the 29 in the solution times the 28 silicate and the 29 silicate in the solid minus the fraction of 28 in the solution. So this is precipitation rate equations. In the same way, you can get the dissolution rate. And be careful, here the precipitation rate, the unit is mole per kilogram per seconds. But when we describe the dissolution rate of a mineral, we use the mole per meter per seconds. So this precipitation rate normalized to the surface of the mineral actually equals the precipitation rate in this system times the mass of the solution over the stoichiometry of this element, silica, times the surface. So if we check the unit, this is mole per kilogram per seconds times the mass of the solution, kilogram. Stoichiometry is unitness, and the surface is micromole, actually equals mole per meter square per seconds. So this is the deduction process of these two equations. But how do we use that? So let's, for example, if we have the experiment going on, and this is our results, and we have the talc in the mineral, and we have the solution 0.6 gram, which is doped with almost 100%. You can say at time 0, the solution, the 28 in the solution is 0, the 29 is 4.5. So the total silica is 4.5. After 5 minutes, if we say the 28 in the solution is 0.46, the 29 is 3.16, and we have this total silica. And this concentrations can be measured by isotope mass. So in order to use this equation, we have to know the mass. Sorry about that. The mass, if we want to calculate the dissolution rate, the mass is 0.6 gram. So which is 0.6 times 10 to negative 3 kilogram. And the stoichiometry is 4 for silica, right? And the surface area in the talk is typically 1.6. Depends on your experiments per gram. And the d delta 28 is actually equals 0.46 minus 1 equals 0.46 micromolar. And the D29 is actually equal 0.16 over 4.5 equals negative 1.34. And the dt is 5 minutes. 5 minutes is 300 seconds. And the dt and the 28 over 29 in the solution at the middle term can be depicted as the 28. So at the middle term, which is 2.5 minutes, the average of the 29 is 0.23. The average of 28 is just one sec, is 3.83. So we got this. And the dissolution, the fraction of 28 in the solid is 0.9223, right? And the fraction of 29 in the solid is 0.0468. And this we also got this. So then we can calculate the dissolution rate. And the same way, if we want to calculate the precipitation rate, we know this mass, we know stoichiometry, we know surface area, we know the d28 over dt, we know this, and the 28 over 29 in the dissolution rate should be 0.9223 over 0.0488. And the fraction of 29 in the solution at the midterm should be, the 29 in the midterm is 3.83, and the total silicate in the midterm is 4.5 plus 3 is 4.07. And this, we already got this. And the fraction of 28 in the solution at the middle term is 0.23 over 4.07. Then we got all the parameters. So the final results for this example are DIS is equals is, if we know that the solution is, if we have the solid 0.02 gram, we know the surface area is going to be and if you put all the parameters in it, you can get the dissolution rate and the precipitation rate. Okay, alright. This is just an example to show you how to use this equation and how to do the deduction of this equation. So our next video is going to be the principle of detailed balance theory and how we use isotope doping method to test it. Okay, see you guys next time.